Howdy folks, I'm just popping in here. I did create an event in Facebook if you're watching this on Facebook Live. So welcome if you're joining me for that, but if not, if you're watching on this on a replay later, welcome. Sorry, I've got my dog just wanting to jump up on my lap because she hasn't showed any interest in me all day, and of course right now is when she wants attention. So sorry, I'm a bit distracted. I got a request from a student to answer a question. So I'll just read out the question to you. It says, "Hi Amelia, I was just wondering if you could give me some tips on how to learn states of matter for elements, particularly when writing chemical equations. I'm struggling to determine what is solid, liquid, gas, aqueous, and it's a requirement for me to write these states when writing chemical equations." So I'm going to actually start this this live by actually going really literal, right? So learn the states of matter for elements. So let's start with the periodic table. So I've got my periodic table here. Okay. So there's a reason why you learn this early on in your chemistry journey, because it's just so invaluable. And I use it in my teaching all of the time. So what you'll see is that what I've done is I've annotated it, right? For most basic chemistry courses, like I pretty much chop off at the lanthanides and actinides and just say, don't worry about those. The likelihood that you will need to worry about them is so incredibly low. And to give you an idea of something that, I've been a chemist pretty much since I started uni. Like that was the science that I loved. And in all of my, how many years is that? 18 years, studying chemistry and using chemicals, the only chemical that I've ever actually used and had to use any of its information for is cerium down here. Okay, so the rest of them I've actually had nothing to do with. So I kind of just chop it off at the bottom there. All right, and what you'll notice I've done, and it's something that people do, like the first thing when they look at the periodic table is they split it off with this zigzag lines. Now, if you go on Google and you look up the periodic table and you look up metals, non-metals, metalloids, okay, you'll find deviations in what this zigzag line looks like. Okay, this is what I choose to do just because it's easy to remember. Like, so I think if you see some people, it goes down 2 here and then across 1 and down 1. Like, it's just a little bit weird. So what I've done, I've just shown that zigzag line, right? So it goes down first and it zigzags down. The ones highlighted in red here are our metalloids. And to be honest, I haven't had a lot to do with the metalloids either. So if I look at them, like I've had a little bit to do with boron, a little bit to do with silicon, a little bit to do with germanium. But other than that, like, you really, at basic level chemistry, you're not going to be asked to have much to do with the metalloids. Okay, so on the left of that zigzag line is all of our metals, right? And so, when you're having to write chemical equations and having to decide whether they're solid, liquid, gas, or aqueous, right? All of our pure elements are going to be solid, liquids, or gas. They are not going to be aqueous. Why? What is aqueous? Well, let's break it down. Aqueous is got the word aqua in it, which means water, okay? And if you have water combined with any of your periodic table of elements, it is no longer a pure element, okay? So it will not be aqueous. All of these in their pure form will be solids, liquids, or gases. So all of these here, I'm gonna pull out 2. So right, hydrogen's an interesting one. So that's usually sort of picked up and it's put in various different places on different periodic tables, but for the purposes of this one, it's up here, right? And then the other one I've picked out is Mercury. Okay, so with the exception of those 2, all of those elements on this side, excluding your metalloids, right? But on this side of this zigzag lines. All of these, with the exception of these two, are going to be solids. And if you think about logically, like if you think about what is the state of matter of aluminium, okay, we have aluminium foil. It's a logical deduction to make. Same with a lot of your transition metals. So if you think about iron, cobalt, nickel, copper, zinc, those kind of metals that you know really well, like in everyday life, they're all going to be solids. Okay, so then let's pull out mercury. Mercury is going to be a liquid. Okay, so mercury, not so much anymore, but they used to be sold in old thermometers. Okay, and you used to be able to actually see the liquid when the liquid expanded and contracted. It actually changed the temperature, right? It's a liquid, so it's actually a metal which is a liquid. That's the only exception to the rule, other than hydrogen. Hydrogen's an interesting one. Hydrogen in its elemental form is a gas, right? Hydrogen gas, okay, very, very flammable as a side note, right? It is in so many ways, it behaves way more like a non-metal, okay? But for the purposes of hydrogen gas in a chemical equation, you're going to find it's a gas, right? So all solids, liquid, gas. Okay, then when we move over to our non-metal side of our periodic table, so I'm coming a little bit closer, okay, let's start with our noble gases, right? Noble because they have a full outer shell of electrons. They are noble because they are non-reactive, right? And they are gases, hence we don't have to remember what they are. They are noble gases. They will always be a gas. You will probably probably so rarely see them in a chemical equation that you probably don't need to remember that they're a gas in a lot of ways, but you do come across them in ionization type chemical equations. So I'm not going to totally disregard them, because you may come across them when you're looking at ionization. Okay, so from here on in, what have we got? In blue here, nitrogen, oxygen, fluorine, and I've put chlorine in that as well. So those four there, they exist in their biatomic form. So N2, and when I write that, it's capital N subscript 2, N2, O2, F2, Cl2. Okay, they're all gases. Okay, so nitrogen gas obviously makes up a large proportion of the gas that we breathe. Okay, oxygen is obviously the oxygen that we need to live. Fluorine gas you probably won't come across very often, like in real everyday life, but you may definitely come across it in chemistry. And then chlorine gas, that's what you smell when you go to the pool, and that's also a gas, right? So then we move down our group 7 elements. So the top two, fluorine, chlorine, are gases. Bromine is a liquid at room temperature, and iodine is a solid. And it's actually an interesting solid because it sublimes at low temperatures. So it's actually used, another side note, it's actually used in some types of fingerprinting. So they heat it up, it sublimes into a gas. So it goes from solid to gas. That's what sublimes means. And then it travels over to the fingerprint, and then it condenses back into the solid on the fingerprint. Small little factoid there. All right. So to summarize, right? Solids, liquid, gas, liquid, solid, gases. Okay. And then the metalloids, most of them. A lot of them you won't find in pure form. So like silicon, you can get silicon's a solid. Most of those are solids though, I believe. A lot of the metalloids I haven't spent a lot of time with. All right, so let me just come back to my notes. Have I mentioned everything? Yes, I have. All right, so now I'm going to move on to, because when I read this question, I was like, so how do I learn the states of matter for elements? And I took that very literally, in the sense that I went, well, we just look on the periodic table and that's all good. But what I have to remember as a teacher is that word elements can be cross-reference when people are talking about molecules, compounds, all that kind of stuff. So I'm going to now switch over to the writing of equations and just expand that a little bit more. Okay, so when we're writing equations and having to work out what the states of matter are for the things in those equations, I guess the first point I want to make is that you really have to use a lot of logic, right? So, and the other assumption I guess you need to make is that unless it's stated otherwise, the states are at room temperature. So when it comes to writing states for things, particularly in equilibrium type questions, they'll say at 400 degrees, la 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 la, and you have to use that logic and go, oh well, at 400 degrees, water is not a liquid. Okay, so really, unless it's stated otherwise, assume that what you're working with is at room temperature, and that also applies to your periodic table stuff too. So I'm going to move on to this. So this is one of my VCE chemistry formula sheets. They are available on my website if they interest you. But I want to draw your attention to this yellow box here. Okay, and I'm sorry, it's going to be a little bit blurry. I'm not sure how clear that is. Okay, I'm actually going to start at the bottom here. So we have our precipitation reactions. Now, you'll notice actually that's the only equation in the entire box here that I've actually got states on. Okay, so what you want to remember, what is a precipitation reaction? And if you haven't covered this yet, don't stress, right? But for those who have covered precipitation reactions before, you're basically mixing two aqueous solutions of salts. Okay, so that gives you a clue already. Two salts in aqueous solution, right? So those two are going to be aqueous. And then what we're forming is a solid. Think about the word precipitate. It means to fall. When we're talking about the rain, and they talk about on the news, they talk about precipitation, and they're actually talking about rain falling from the sky, from the clouds to the ground. So what happens in a precipitation reaction is that we mix our two ionic compounds. So we mix them and we form a solid because that ionic compound that's formed is actually not soluble or does not dissolve in water. Okay, so then it kind of comes back to you knowing precipitation rules and solubility rules. Okay, but if I come back to this equation here, right, AB plus CD, whatever they are, whatever those ions are both aqueous. Okay, you form your precipitate here, so that has to be a solid. Okay. And then your other one, I've never come across it. I mean, I'm sure it's possible. But in basic level chemistry, you will not form two precipitates. One will be a precipitate and one will be aqueous. And I guess that's something that I can cover off in a different video. There's lots of solubility rules and they can be quite confusing. And if you look at the table, you're like, oh yes, well, this is soluble, but not with that, and la la la. So I might come back to that. There is an easier way to deal with those solubility rules. If that interests you, just leave a comment underneath and I will come back to that one. Okay, so that's our precipitation reaction. Let's come up to our combustion reactions. So basically, let's go with the top one here. Okay, combustion meaning burning something in oxygen, whether it's a metal in the case of the bottom reaction, so metal plus oxygen, or it could be a log of wood, in which case a log of wood comes under this one here, carbon compound. Okay, so carbon compound plus oxygen. That carbon compound can quite often vary whether or not it's a solid, liquid or gas. It won't be aqueous. But depending on like something like ethene is a gas, if you go down to octane, that's going to be a liquid. And if you go down to that has like 20 carbons, it's going to be a solid. So that's about the only one that you probably, again, use your logic. You think of something like propane gas. Okay, you have to use your logic. Quite often in a question, they may even say what state it is. Okay, so whatever that state one is, what that state is, plus oxygen has to be a gas, right? And then we've got carbon dioxide and water. And if you look underneath there, metal, again, your metal's probably going to be solid. I don't know whether we could do this one with mercury. I'll find out. But whatever metal that is, would be a solid. Oxygen would be a gas, and then your metal oxide is usually a solid, right? Your carbon dioxide and water, though, this is the more common one, the top one. Okay, that one, your carbon dioxide, again, use your logic. We breathe in oxygen gas, we breathe out carbon dioxide gas. Okay, and then the only one that could get tricky there is our water. Think about if we burn a log of wood, do we see liquid water? Well, only if the log of wood is extraordinarily wet, but think about if you go with a dry piece of wood, that water actually is going to be in a gaseous form. Okay, so we don't see water sort of pouring out of a fire. Okay, it's in a gaseous form. Hope that makes sense. All right, so then we come up to these top 6 equations. Now, if you haven't done acids and bases yet, again, don't freak out, right? But what I want you to take away from this, all right, so let's start simply. So there's 6 equations. I kind of bulk them down into 4 though. So if we have our acid, so whenever we see an acid, usually an acid is aqueous. It's very rare that you may come across a liquid acid. I think just because they're so strong and to produce a pure liquid acid is actually quite difficult. So we don't actually use that. When you buy like concentrated hydrochloric acid, like comes in about 32%, and that's as strong as you can buy it basically. So they're not going to be pure acids. Okay. When we have the top one there, acid plus metal, okay, metal's always going to be solid. If we go to the next one down, so metal hydroxide, and the next one down there, metal hydroxide or metal oxide, okay, they will always be a solid, okay, so you're adding an acid to a solid. And then if you look on the right hand side, those top 3 make a salt, okay. Now the salt, because it's been formed in our acid, which contains water, it has to be aqueous, has to be, okay. And then also, because in the second 2, so the second and the third one, the product of that is water. So not only do we have the water in our acid, we're also producing water. That salt then has to be aqueous, has to be, okay. The one at the top there, H2, we come back to our periodic table of elements. It has to be a gas. All right. Then we look down to our next one. So we have acid plus metal carbonate and acid plus metal hydrogen carbonate. So whether you have a hydrogen carbonate or just a carbonate, you are always going to get, when you mix it with an acid, you're always going to get salt, water, and carbon dioxide. Same deal applies, right? Your salt has to be aqueous. Your water is going to be a liquid, obviously, and your carbon dioxide gas. So when you do these reactions, so I'm about to do this live for another project I'm doing, right? You mix vinegar and sodium bicarbonate, you get a whole lot of fizzing, and that fizzing is your carbon dioxide, okay? So that one obviously is going to be a gas. And then the bottom one there, acidic oxide. This one I don't come across very often. Acidic oxide plus a base. Okay, so your acidic oxide is probably going to be, you'd probably be told that one, to be honest. And your base could be solid or it could be aqueous. So think about sodium hydroxide. Sodium hydroxide comes in little pellets. So they do come solid, okay, depending on the base, right? Ammonia, if you think logically, is a liquid, but it also, you know, same sort of deal, right? It comes aqueous. So when you get it delivered, like we used to get delivered at my old work, 25% ammonia, okay? And that's super, super, super strong ammonia, right? So usually your base probably will be aqueous, I think. And even then, like something like sodium hydroxide, yes, it comes in a solid. If you leave the jar open on the bench overnight, it'll come in, it's a liquid mess because it's what we call hygroscopic. So it actually absorbs water out of the atmosphere as well. So, all right. So those two could be, you know, your acidic oxide and your base could be quite variable. But again, your salt is going to be aqueous because your other product there is water. Okay. So I think I've kind of covered that off. I guess what I'd go back and say, right, is the main points I want to make is use your logic, assume it's at room temperature unless you're told otherwise. The second thing I would definitely say is writing equations is a practice thing. So on the back of this formula sheet here, I actually have a table. So that big green table at the bottom there has all of the basic cations and anions that you may use in ionic equations. Okay. So I usually say to my VC/HSC students, international baccalaureate students, my first year chemistry students, learn this table. And it's probably another video I could do to show you guys through this table and why I've set it up the way it is, because it's much less labor intensive to remember what's in that table if you have a system to read it. Okay, so that's something else. But again, that's learn these cations and anions. I can't, it's one of those things people say, how do I make this easier? Well, that table, the way I've set it up, is probably the easiest you'll ever make it, because otherwise you're usually not given that in the exam, and you basically have to remember them. There's not much wiggle room on that. And then you start thinking about, right, with your combustion reactions, you have carbon compounds, which again, you'd only have to worry about that when you get to your carbon chemistry unit. And again, it comes down to, you're probably not going to be given this table here. So I've tried not to include stuff that's in the formula sheets from the examiners, right? So in the data books that you get from the examiners, I've tried to include in these formula sheets all the other things, right? You're probably not going to get this, right? So when you're writing your carbon compounds, you need to actually know how to write them. So you need to know that octane is C8H18, and then to know, okay, well, what do I know about the properties of 8 carbons in a row, and how well are they going to have intermolecular forces and all that sort of stuff, and then deduce, it's probably going to be a liquid, i.e. petrol. If you know that octane is petrol, you're sorted, because you go, oh, that's a liquid, right? So you try and make as many of those connections to everyday stuff that you absolutely can. So what did I say? Assume room temperature. Know, your basic cations, anions, your basic carbon chemistry stuff. And that's the thing, I guess, with chemistry, it all interlinks. So, yes, it feels like you learn one thing and you go, oh, well, I'll just put that over there now. I've learnt that. I've done the SAC or exam or whatever it is on that topic. We'll just go and put it over there. We don't need it anymore. It's not like that in chemistry. It all interlinks. and you have to keep coming back to this stuff. That's why I wanted to start with the periodic table, because you keep using it and you need to keep going back to it and referencing it. And it's actually a really great tool because it means you don't have to remember stuff. It's really great like that. So I guess, let me have a look at my notes. Yes. And so the last thing I wanted to say, it's all practice, right? Writing equations is not one of those things that you can just have a look at a couple of times and expect that you can do it. You need to do them over and over and over and over and get as much practice as you can to be able to write equations and get those states correct. And again, I'm going to say it again, use your logic. All right. So I'm going to do a super duper quick plug for these, because like my purpose in being here is to serve you guys. It's actually not to sell stuff. I'm trying to be as helpful as I can. These are, so there's also a year 12 version of these formula sheets. So I'll just give you a quick little view. You can have a look on my website. I get to do a bit of a tour of those on my website. So 4 A4 sides for you to basically use as a quick reference tool when you're studying for exams. So rather than having to go through all your textbooks, you've got 4 pages. You can print them out. They're a digital download, so you can access them on your iPad or your phone or whatever. And yeah, so they're $20 if that interests you. If it doesn't, that's totally fine. I'm not here to sell. I'm here to help. So having said that, I would love you guys to please send me requests on topics you'd like me to cover. So this question actually didn't come from this group, but I thought it'd be very helpful to you guys. And what I'm going to do, so I'd love for you to send me a private message if you've got a question. You can also, if you want to leave a comment in the group, like a post in the group with a question and a picture, or I can't do this question, can you help me? Like, I'm very open to that idea. But if you're not wanting to identify yourself, that's also fine. So send me through a message to my page, The Zen of Chemistry, and I'll come back here and pop back in here and answer your questions. So it's Good Friday. I hope you're actually having a really relaxing time. This is actually what I do for fun on my days off, as you do. So I hope you have a great Easter. I'm not sure when I'll pop in here again, but please use me as a resource. Please ask your questions that you might have already asked your teachers. I know in Victoria here we are transitioning to a lot of online learning. So that will mean a lot of people staying home, doing whatever their teachers are able to provide to them from home. So use me as a resource to help you out. Use me as a resource to just another person to bounce off of. When I was studying third year chemistry, I actually had a teacher that I really didn't gel with. And so what I ended up doing, we had an assessment and we had to, obviously learn all the stuff before the assessment, and I just couldn't understand a word this guy said. So what I spent my time doing was actually went to the library, back when everything was all paper. That dates me a little bit. And I went to the chemistry section. I went, right, I'm looking at this topic. I went to 10 different textbooks. I photocopied the section from those 10 different textbooks, went through them, and usually one of them gave me an idea or an understanding that spoke to me in my language. So I hope to be that resource for you if you're struggling with whatever resources your teacher is able to provide. I want to be just another one of those resources. So please send me through questions, and please, if you found this useful, please engage. I really want to see comments, even if it's just a simple thank you. If you watch this far, please, I love the feedback that you guys give me, and I really want to hear it and see it, and I want you to query me, why is that, okay? I want that interaction. So hope you have a great Easter or whatever you celebrate at this time, but it is a quiet time here in Australia, just a time to chill out and do what you do at Easter. So I hope you enjoy yourselves, and I'll see you soon. Bye.